It's data that corresponded to a constant velocity. So this is a graph of position versus time. And in the position time data table, we saw that the gaps in the position were the same gaps for every second, 5, 5, 5. That corresponds to a slope of 5 every time. And physically, that corresponded to a velocity of 5 meters per second, and it's constant. We define that the slope between any of these 2 points will be the same, here and here, 4 to 3, 5 to 4, all, the slope is the same. The same line, the same slope exists. So therefore, the same velocity exists for all points. That means we have a constant velocity that looks like this. It's going to start 5 from 0 and continue to infinity, if possible. I also saw in the velocity time graph of the homework that people started from 0 and went up. No, it's a constant throughout, because every time you have this line, you're going to have a constant value everywhere. There's no starting and stopping. So it should have been a straight line. A few of you did that correctly. That was for the acceleration time. So we're about to do that now. And then for this particular graph here, this configuration, it's velocity versus time graph has no slope. There's no slope here, so therefore there is no acceleration. So every time you're going from position time graphs to velocity time graphs to acceleration time graphs, in other words, you're going down from position x, v to a, you're taking slopes of all of the data in that particular graph. The slope of a position time graph gives you the velocity time graph. The slope of a velocity time graph gives you acceleration. There's no slope here, so therefore there's no acceleration. You know, so, and when we go backwards, a, v to t, we're gonna do something special called an area. Real brief to get that fourth equation. So, okay, like I mentioned, the slope of a position time graph is the velocity, but the slope of a velocity time graph is the acceleration. And very few times we have slopes of acceleration time graphs, but that's very rare cases. I also gave you the formula for your acceleration. So now we went to acceleration here and giving you the quadratic formula to help you get the values in x versus t. That would help you populate your velocity time graph and your acceleration time graph, which was part of the homework. So let's do that formally now. Okay. So notes begin. So now we're going to be accelerating towards the east, right? One of that old school homework where I had the 10 scenarios. And let's dissect that guy. So we're going to be accelerating in the east region only. And increasing position. So we've seen this guy times. So we have a data table. That's our claim. We'll get our data. We've now conducted the experiment and we have generated or recorded these values that I'm going to write up. But we're actually going to be generating the values because we're not doing the actual experiment. So we're going to get a theoretical set of values for every second of time. So, okay, 0, 1, 2, 3, 4, and 5. So I gave you the formula y equals x squared because the gaps in position indicate a quadratic function. So that's something on the back end that we don't have to worry about here. We could derive it, but that's not important for our cases. So in math, it's y equals x squared or y equals ax squared plus bx plus c, the quadratic function, but we're just going to use this part of it. Keep things simple. Now this is the math version. We know in physics that corresponds to the variable that exists in the y-axis, which is position. So x equals the variable in the x-axis, which is time. So it becomes x equals t squared. Still a quadratic function, but just real physical variables. So now, in order to generate all of the positions, we have to plug in all of the times here. And that becomes x equals 1 squared, which is just 0 here. And this is going to be 1. So this is each position. X is a function of time. And say first position, or technically second position, but you know, this first non-zero value. So the second position is 2 squared. That becomes 4. And then x3 is just going to be 3 squared. That's 9. And you get this point. 4 squared is 16. And 5 squared, 25. Just to be visual about it. 4 squared, 5 squared. Right, and so on. And then from there, we know that by definition, if I want to get my velocity values, I need to take the slopes at each of those moments. Velocity is measured in meters per second. Time in seconds. So I know that my velocity is going to be increasing from 0 to large. We've seen the situation for this, for these curves. But before I do that, let me just draw the graph of this so we can have a visual reference. I can get all the data and then draw the graphs. But okay, so we have all right. So we have position meters, time in seconds, and we know that this is going to grow quadratically. It's going to be a quadratic function, something like this. T equals 1 all the way to 5 for all of these positions. I'll make that a little bit fatter. Like that. And we can scooch over here. Again, you know, it's rough. You can plot the points if you want to, but we know that this is the nature of the function here. In math, it would just be y equals x squared, where a is the constant ax squared. But in physics, we translate that to position in meters equals time squared measured in. All right, and we know already from first principles that each point is going to have a different slope. So it's not, so we have, if we were just to plot them, very rough. if we're just eyeballing this, we can clearly see that the lines between the 5th point and the 4th point is going to be different from the 2nd point and the 1st point. They're not in this, they don't have the same shape. So therefore they have different slopes. And these slopes are going to be increasing in value. And last time we drew the cumbersome tangent lines to give a visual as to why or how those slopes are going to be different. They're going to not only be different, but they're going to be increasing in value. The slopes are going to be going from 0 to large. Seen that before with acceleration. Slopes go you go from 0 to large. And by definition, the slope of a position time graph is the velocity. So the slopes in math become velocity in physics relative to position time, only when looking at position time graphs. So slopes go from 0 to large, and then those slopes in physics are velocities. Okay, so they grow when the object, whatever it is, a car, yourself, anything is speeding up. So the velocities increase. You're gaining speed, but the acceleration is constant. Your foot is steady on the gas, but your speedometer is increasing in values, 20, 30, dramatically every second, 45. It's increasing in value. Well, it's a steady increase actually for velocity. So, and the acceleration will be constant. But the position is going to be dramatically increasing. It's not, the gaps in position are not going to be equal. So we have 3, and then we have 5, and then we have 7, and we have 9, and so on. Now, of course, those are the values that I gave last time, 5, 18. They can work, but for different time values. So we have to generate those particular set, if that is a set, by this equation. So if I gave one person in your group, when we get back to the project, okay, give me your positions for this set of data, very easy. But if I give another group member, say 5, 10, 15, 20, then the positions, of course, would look dramatically different. So I'll be doing that in the future. So this right here is important because it helps us to get an understanding of what the velocities will do in the velocity data table as well as the velocity graph. So again, now let's go to our velocity versus time data table. So we're going to start from 0. Because of our stipulation, because of what we know a priori from our definition, the first velocity will be 0, and then it will start growing, go from 0 to large and large value. 0 slope, starting to increase more and more and more and more and more. All right. So let's now get the slopes of each one of these points. I guess I'll just do that on the side here and then just populate the table. Okay, so first velocity is 0, so I can just go ahead and say the second velocity would just be the slope of the second position minus the first. So they're going to be 1 minus 0 divided by 1 minus 0. So I'm just taking these two values in position, 1 minus 0 divided by 1 minus 0 in time, because we know already that velocity is position over time. That's going to give me a value of 1 meter per second. And of course, it's positive. It's in the east domain. And And that's going to be our first value here for the first second. Now for the second, or these, second, the third velocity. It's going to be 4 minus 1 over 2 minus 1. And that's going to be 3. Let's go ahead and say plus 3 meters per second. And then we can kind of get a feel of what is going to happen. But I'll do one more to give you, convince you. Okay, so a little smushed here, but all right. So the fourth velocity, 9 minus 4, these two values, 3 minus 2, plus 5, and 7, and 9. You can see the gaps are equal to each other. Continuous there. So 1, 3, 5 for the third second, 7, and 9. So now we can see that the data for velocity versus time, the gaps are relatively the same. We can go from, it's like at least definitely from the first second. So because 0 is immaterial, we know it's going to start from 0. So our real, our important starting point would be the ones. So from the 1 second, it's going to increase to 3. The gaps are 2 meters per second every second. So a gap of 2 meters per second, 2 meters per second, 2 meters per second, 2 meters per second every second. So that means our acceleration should be 2 meters per second squared. But we're going to verify that. So I think, let me go ahead and do my accelerations on the side. So acceleration, from first definition we saw up top, acceleration is going to be the slope of all of these values, the slope of velocity time graph. In this case, the acceleration will be the slope of this velocity time data. And this acceleration will be constant. The gaps are constant. So therefore, our acceleration is going to be a constant value. But I guess before I do that, let me just go ahead and graph the velocities and then just keep it consistent from before. So time is there, velocity meters per second. And so the first second we have 1 here, of course, 3, 5, 7, 9, sequence. So it's a constant slope, so there's no breakage here. It's going to be the same slope for all of these points. We know that it's going to be a line because the gaps in velocity are the same, so it's just going to be a best fit line, something like that. Perfect. Remember, best fit, not perfect fit, best fit line for velocity. Now we can just do our slopes of velocity versus time, but in this case, we know it's just going to be one slope because it's one constant value for all of the points. Okay, so let's verify that. So for the first acceleration value, we can just say 1 minus 0 over 1 minus 0. And that's going to be 1. Meter per second squared. Our second acceleration value is going to be say 3 minus 1 over 2 minus 1. That's going to be 2. And so I know that so it's going to be positive. I know that this is, yeah, I know that this is a little bit of a deal that, you know, some people put this in their homework. But I would just go ahead and say, you know that this slope is going to be one constant value. So the most important thing to look at is in this velocity data table, we're going to start from the ones. And the only reason for that, I mean, there's a calculus reason why, but again, we're not going to discuss that here. So all of us are in calc. But we're going to start from 1, and to show that the slope is indeed constant, we know it's constant because all this data is linear. And so we're just going to get one final value for all of these points. So we're going to start our tracking from the first second and not the 0th second. So we're going to go from 3 minus 1, which we just did, over 2 minus 1, and that gives us 2. And then 5 minus 3, 3 minus 2, and so on. So that's going to be 2 meters per second squared for our first acceleration point, our important acceleration point there. Then A3, or I'll essentially say A2. So that's going to be 5 minus 3 over 3 minus 2. 2 meters per second squared, A3. 7 minus 5, 9 minus 7, the whole thing. So you get the point there. All right. And A4. Yeah, 9 minus 7. Because again, we know the slope is constant. One constant value, that's going to be a horizontal line, no breakage. There was no starting and stopping. It's continuously rising at a constant rate. of 2 meters per second squared. And so that goes for all time. And so we can just arbitrarily draw a horizontal line like this. It's 2. So that's what you should have had for your homework set. I will allow if that little break happens for the first second, but it can't go any more than that. So I'll be lenient on that part. But it should be a constant horizontal line because the acceleration is in fact constant. What about D? Always. Yes. All right, so hopefully we got that locked in. And then, oh, okay. Now let's write down those kinematics equations. I think I'll do that. Yeah, I might as well do that, do some exercises. So the second part of the homework was to write down all the 4 kinematics equations in the x direction and the y direction. So I'm going to complete that for you. So whatever you have down, I'm just going to take it for credit, but we're going to be clear here. The book was, I wouldn't say unclear, it was just incomplete on that. All right, so let's talk about these kinematics or motion equations, and then we'll do some motion examples and our pickups and stuff. So you should have seen this equation in your section 2, some form of this guy. So delta x equals EIT plus a half AT squared. I'll explain what they mean in a moment. So I'm just writing them down, and I've derived the 4th one, and then we'll dissect them all. We got another equation for final velocity. V final equals VI plus acceleration times time. And we had a third one, V final squared equals VI squared plus 2a delta x, 2 acceleration delta x, 2 times the acceleration times delta x, which is the displacement. And so the 4th equation, which the old book was very clear on deriving, we get the 4th equation from looking at the velocity time curve in while this object is accelerating. So we're going to take the curve that we drew before for velocity, which was an increasing slope, increasing values. The velocity is actually growing. And what we can do is we can actually derive or come up with the 4th equation from this graph alone. And we have to do something special. So before, in position time, we know that the position time graph is going to be a curve. The velocity time graph, the slopes of those guys are going to be increasing. So we have an increasing line like this. And then just as we did, take the slope of this line is going to be a constant value, a straight horizontal line in acceleration. So we stipulated that the slope of position versus time is the velocity. This should look somewhat familiar to the slope equation when we have m equals change in y over change in x. Just write that here. Anytime you have a division in physics, that's a slope, every time. So we are going to be applying a lot of the things that you did arbitrarily in your math classes in physics. So these velocity, delta x over delta t is a slope equation. Acceleration, velocity over time is a slope equation. Acceleration is force over mass is a slope equation. Any division is a slope. So acceleration, likewise, when we take the slope of velocity versus time, that's going to be a slope equation. Acceleration delta v over delta t, that's a slope. All of these guys are slopes from what you learned in algebra, rise over run. M, y equals mx plus b. There's no y-intercept, y equals mx. Intercept is 0. So when you want to say, calculate, use this velocity time graph to come up with the last equation, which is a displacement equation, we have to do something special. We don't do slopes anymore. So let me visualize this for you. X versus t to v versus t. I guess I'll do it here. Span this guy. To a versus t. When you go from x to v to a, as mentioned, those are slopes. X, v, a, you take slopes. Now, what you can do when you go from a to v, x, we have to do areas. So if I want to go from v to x, which I need to do in this graph here, I have to take the area underneath this curve, underneath this line. What does that look like? Well, we have to capture both endpoints underneath this line. And when we do that, we are going to form a right triangle that looks, something like this. We're encapsulating the initial velocity here, which is 0. So we can just say vi equals 0 here, or just vi. And since this is a velocity line, this point here will be the final speed. So we've gone from some initial velocity, in this case 0, to some large velocities. Some final velocity, it could be anything, 20, 10, 5.3, whatever it is, it's a final velocity. So what we formed here is a right triangle. Anybody remember the area of a right triangle? This basic formula for that.
Base times height divided by 2.
Yes, 1/2 base times height. So we're going to take the area of this guy. The area of this right triangle here will give us the displacement, or the last formula that we need for our motion equations, and then we'll look at some examples of that in section 2. All right, so let me erase this part. So keep that for a moment. So area of this right triangle will be 1/2 the base here times this height. So height here, base there. Now on the x-axis, we're going from initial time equals 0. That's why we had that first point in velocity 0, 0. Most of our data charts say 0, 0. We're going from ti equals 0, x-axis, to some final time. Who cares what it is? It's just t final. No, it's not 0. So in math, this, arbitrary 1/2 base times height, but we translate that physically to this form here. So we got 1/2. The base here will be, an addition from the initial time to final time. So it's going to be 1/2 the base, which is delta t. And the height here will be the sum from the initial velocity, because now we're on the y-axis. We're going from the y-axis here, vi equals 0, all the way to v final. So vi plus vf forms this height. We must add in order to get this height. So instead of h here, the height will be vi plus vf. So this area that we know in algebra, geometry, translates to be our displacement. Let me write up the velocity equation yet again. We know that this is a slope equation. So if I want to solve for a displacement here, I say delta x is going to be velocity times delta t. Every time I see a multiplication, that's an area. Every time I see a division, like this velocity equation, that's a slope. We're translating slopes into actual formula, physical formula, and areas into actual physical formula. So this area here, which is 1/2 vi plus vf delta t, translates into a displacement. We know that velocity is delta x over delta t. This is what we get here. The area underneath this line is your displacement. Why is that? Because when we rearrange the equation, we see that delta x is going to be a multiplication, just like we have here. 1/2 base times height gives me a displacement. If I were to take the area of an acceleration time graph, okay, let me just go one step further. So a equals delta v over delta t. That's a slope. If I want to solve for velocity, velocity is going to be a delta t. This is an area. So in order to get this formula, I have to take the area underneath the velocity or the acceleration time graph. I'm not going to do that. It's not important for here. So every time you have a division, that's a slope. Every time you have an area, every time you have a multiplication, that is an area. This particular area is your displacement of this velocity time graph. So to be complete, so the area that we took here is going to be 1/2 base delta t times the height, which is the sum vi plus vf. That area translates into a displacement. Delta x is 1/2 delta t vi plus vf. That's our fourth equation. Don't worry about it. If you didn't get it, I won't mark you off. So let's put them all together. Delta x vit plus 1/2 kt squared. Vf equals vi plus kt. Vf squared equals vi squared plus 2a delta x. This guy is, doozy to derive. I won't even do that here. And I'm going to rearrange the above equation to make it neater. So delta x is going to be 1/2 vi plus vf times delta t. Now let's take a look at these guys and dissect what they mean here. So this first equation here is going to be, I can find my displacement when I know all of these values. So let's say the first equation here. So I can find displacement. This is finding displacement when I know my initial velocity, my time, and my acceleration. I'll just so displacement when these guys are known. And you can even use this first equation to find acceleration if you know delta x, velocity, and time. So that sort of thing takes some practice. So we're going to do some couple of examples of those in section 2. The second equation here, V final equals VI plus KT. VF is final velocity. I can find final velocity when initial velocity, acceleration, and time are known because this is equation here. I want to find my final velocity. Well, I can find it if I know my initial velocity, VI, my acceleration, and my time. And technically, this would be a delta t. I get glib and write it as that because I've been writing t forever. So let's just be totally basic on this. So let me, yeah, that's just me years of writing this as t, knowing that it's delta t. But anyway, let me not be glib with that. Technically, this is the time interval because it takes time to change anything. It takes time to change position, the delta x, the velocity. This is technically a delta t, but you can see it gets cumbersome after a while. But anyway, we'll write it there for now. So this will be 1/2 a delta t squared, where delta is final minus initial. I'll just put a small plus to somewhat distinguish it from the capital T for time. And likewise, this equation here, instead of just T, it's understood delta T, but is, let me write it there for right now, a delta T. So this is final velocity when I know my initial velocity, acceleration, and my time interval, not just one time. It takes time to change anything. Okay. Delta T are known. And then, let's see, next equation, and in no particular order. This will be the third equation for now because I wrote it third. Okay, so this is VF is final velocity. Just keep it here, equals initial velocity plus 2 times acceleration times your displacement. So I can find my final velocity when I know my initial velocity, acceleration, and my displacement. Let's see. It's all about when you read a problem, when you see a couple of these in a moment, read the problem, figure out what you know about the problem, and then choose the appropriate equation. Challenge your thinking, of course, because you need a challenge. Nothing's going to be cookie cutter. This is the way the world works, but we're going to get some basic ones, hopefully basic enough, and then start building on it. So it's final velocity when I know my, when VI, acceleration, and delta X known. You know all three of those, you can use this equation. All right, well, if I just know my initial velocity, acceleration, and time, I can find my final velocity using this equation. If I, just know my initial velocity, time, and acceleration, I can find displacement. Then the final equation, delta X, 1/2. But if I just know my two velocities, my initial, my final velocity, and my time, I can use this equation to find my displacement. So this is, hang in there. I know this is quite much, but almost there. So this displacement equals 1/2 initial velocity plus final velocity times delta t, which is my time interval. I'll just say time because it's a time interval, delta t, final minus initial. All right, any questions thus far on the equations at all, the meaning of which variable means what? Break. So again, I just want to, get that last equation, put them all together. These equations of motion are the kinematics equations, only exist for the horizontal x-axis. As I said also in the homework there, the same equations exist in the vertical y-axis, but we have to change two variables. Here is what we do. Let me see if I can do these side by side. All right, so I wrote up this guy, delta x, vi. I'm just going to write this t. T means final minus initial because it just gets cluttered. Please ask away just in case you missed why I'm writing just t. It is delta t, just make it cleaner. Delta x vit plus 1/2 at squared. This up loud right here. This one is hanging out there, so I'll just use your, best judgment, right? Okay, so the VF, VI plus AT, that's nothing changes. It's delta T all over the place. And even I get glib here sometimes, but right now I'm just going to say delta X. Sometimes I say 2AD, 2AX. After a while, with practice, you should get free like that. Will be. Okay, so now in the vertical axis, these same equations, but when an object is in free fall, these equations take a different form. Instead of going in the x-axis, we go to the y-axis. And instead of saying a common acceleration A, the only acceleration in the vertical axis would be what? If something falls, What's causing it to fall?
Gravity.
Gravity.
Gravity is pulling it down. The force due to gravity is pulling it down. So we change our acceleration variable here to negative g. And the reason why it's negative g is because gravity is pointing downward. Okay, so that's the transformation that we have, the two transformations. We go from delta x to delta y, and everywhere we see a, we make a minus g. So delta y is vi t, and it's going to be, I'll factor out the negative sign, so it's going to be negative 1/2 g t squared. So don't make the mistake of saying minus minus. Okay, I factored the negative already out. So that should be plus 1/2 negative g t squared. When you factor it out, it becomes this clean. Here, it's the same, nothing changes. Well, the only thing that changes is delta x to delta y. So delta y is 1/2 vi plus vf delta t. Now we have a here, so we say vf with vi minus gt, and vf squared minus 2g delta y. So everywhere we see delta x, make it delta y. Everywhere we see a, we make it negative g. So those are the same equations, same form, in the vertical axis. This is the x-axis over here. So this is the x direction, y direction. Free fall, objects falling down under gravity. Here's just any acceleration. Acceleration caused by friction, acceleration caused by putting your foot on the gas, pushing or pulling, any acceleration. But neglecting air resistance, the only acceleration in the vertical axis is gravity. Okay, so that's the complete picture of all those equations. Let's take a breath, and we're going to now go to a couple of questions, problems in our book, in our text.